thanking the organizers for organizing this wonderful meeting and for giving me the opportunity to present my work. What I will be talking about today was completed in collaboration with Antal Levitsky. It's been posted on the archive and published in JHIP. Okay, so what is the basic question that we want to answer? So to motivate it, I'm going to remind you that when we look at the quantum mechanics of a single n by n Hermitian matrix, with the matrix X transforming in the adjoint of the gauge group, if I ask what is the space of gauge invariant operators, it's given by polynomials in the eigenvalues, or equivalently, by polynomials in these traces of x to the little n, where little n can go from 1 up to capital N. This description in terms of the eigenvalues is extremely useful, and that's one of the reasons why we can actually solve matrix models. The question that I want to answer for you today is, let's look at the quantum mechanics of D matrices, XA. Each matrix transforms in the adjoint of the gauge group. For this multi-matrix model, what is the structure of the space of gauge invariants? And in particular, what is it that replaces the eigenvalues of the single matrix model? So that's the question that I'm going to try to answer. I'm going to start off by describing a counting problem that is going to motivate most of what comes. Then I'm going to tell you what the result that we obtained is. I'll then give you a careful problem statement that I will solve in the case of one matrix, and then with the help of the Moline-Weil formula, I'll solve it for the case of 2 and 3 matrices, and then I'm going to summarize some general lessons that we get from this work. So here is the counting problem that we're going to study. So we've got two variables, x and y, and I ask you how many degree D polynomials can you construct from those two variables? At degree 0, well, there's just one, it's 1. At degree 1, it's x and y. At degree 2, it's x cubed, xy, y squared, and so on. And what I want to get hold of is this numbers, this 1, 2, 3, which counts the number of degree D polynomials. So how do I do this counting? Well, I can take 1 over 1 minus x times 1 over 1 minus y, expand each of those factors, and then multiply the two brackets. And what you notice here, I am generating exactly all of the polynomials that I listed, and I'm generating each of them with a coefficient of 1. So if I now set x equal to y equal to t, what I learn is, from this expansion over here, the coefficient of t to the n counts how many degree n polynomials I have. So at degree 3, I had 4 polynomials, and here I've got a 4t cubed. This series is known as the Hilbert series. It's a standard tool in invariant theory and in graded rings. And if you expand the Hilbert series, the coefficient of t to the n just counts how many degree n polynomials you have. I was generating my polynomials from x and y, and you'll notice that the Hilbert series, in the denominator, I've got a product of two factors, one factor associated to the x and one factor associated to the y. Let's make it slightly more complicated. So now let's count polynomials generated by x1, x2, x3 squared, x4 cubed. So I've got 4 generators, and they've got different degrees. I've got 2 generators of degree 1, so I've got a 1 minus t squared. I've got a single generator of degree 2, so I've got a 1 minus t squared. And a single generator of degree 3, so 1 minus t cubed. So again, a factor in the denominator for each of my generators. And arguing exactly as I did on the first slide, if I make a power series expansion, the coefficient Cn of t to the n counts how many degree n polynomials I have. Now, this counting problem that we've looked at so far has been the simplest kind of a counting problem you can think of. The generators have all been free. There's been no relations between the generators. And that's not the general structure that you see. To see something that's slightly more general, let's imagine counting spherical harmonics in d dimensions. In this case, we're counting polynomials constructed from x1 up to xd. So your first reaction might be, well, we've got d generators, each of degree 1. So the Hilbert series should be 1 over 1 minus t to the d. And that's wrong. So why is it wrong? 1 will be counted. That's the spherical harmonic of angular momentum 0. But the sum of the squares is also angular momentum 0. So I shouldn't count it again. Both of these count as the angular momentum 0 spherical harmonic. So I should actually impose this condition so that I'm not overcounting. So I've counted too much, So what should I do? I should subtract something off. That's why I've got a minus sign now appearing in the numerator of a Hilbert series. So that's going to subtract off my extra count, and it's a t squared. Why does it appear like that in the numerator? It's because I did a severe overcounting. You see, I counted 1 times any polynomial, and I counted the sum of squares times any polynomial. So by subtracting t squared in the numerator, I completely correct that error. Now, this is still not the general case. In general, I may have generators with many constraints amongst them. So I'd need to subtract off a term for every single constraint. And now we get to the second place where we can make an error, because those constraints might not be independent. So in the same way that the generators weren't independent and we overcounted, now when we subtracted off things for the constraints, we subtract off too much. And we'll subtract off too much whenever there's a relation between the constraints. So now we need to add something back in that tells us about the relations between the constraints. But the problem is there might be relations between the constraints. So we added too much back in, so now we need to subtract something off. So the language that mathematicians use for this, constraints between the generators is the first syzygy, relations between the constraints is the second syzygies, and so on. So you can have first syzygies, second syzygies, third syzygies. You add them with pluses and minuses in the numerator of the Hilbert series. You might be worried, does this go on forever? One of the powerful central theorems in this area, Hilbert's syzygy theorem, tells us that the depth of this syzygy structure is controlled by the number of generators. It's equal to the number of generators. So it does truncate, but you get a series here. It's always going to be a rational function, but the numerator will be 1 minus stuff, plus stuff, minus stuff, and so on. And that's the general form now of the Hilbert series. So I just told you that so you know the general form. The good news for us, we will only be dealing with freely generating things today. So we don't need to worry about that. Okay, this is the most important counting problem. So I'm going to change the rules of the game a little bit. I'm going to build polynomials. I can use x and y freely, so raise those to any power. And then there's a second set of objects, 1 w squared v cubed. And I must use exactly one object from the second set and only one object from the second set. So now the polynomials I can construct is 1 times anything I can make out of x and y, w squared times anything I can make out of x and y, and v cubed times anything I can make out of x and y. And expand those just like we did on the first slide. We've generated every polynomial we can construct exactly once. So again, put all of the variables equal to t, and we'll get a Hilbert series that counts the number of polynomials we can make with those rules. So just to check that I'm not conning you, 7t cubed, that would tell us that there's 7 polynomials we can construct of degree 3 from the first term with the 1. What are the degree 3 polynomials? X cubed, x squared y, xy squared y cubed. From the w term, there's going to be a w squared x, w squared y, and from the last term with the v cubed times 1. So a total of 7. Good. That's that 7t cubed that we see sitting over there. So in this case, that's the structure of the Hilbert series. So this I want you to remember. So let's summarize the key lesson. We're talking about, this is actually called a module over this ring. So we're talking about a module. These are the generators of the module, 1 w squared v cubed over that ring of freely generated things. So the polynomials that we've got are being generated by these 5 generators. And the first set of generators, I can act freely with those. I can raise them to any power. Where do they appear? In the denominator of the Hilbert series. The second set of generators I'm allowed to use exactly once. Where do those appear? They appear in the numerator of the Hilbert series. So our full set of polynomials takes this form: 1 times x to any negative power, y to any negative power, union w squared times the xy polynomial, union v cubed times the xy polynomial. The xy are coded into the denominator of the Hilbert series, and the 1 w squared v cubed are coded into the numerator of the Hilbert series. So what does this have to do with multi-matrices? So I'm going to study multi-matrix harmonic oscillators. If I'm doing that, I want to calculate the partition function. That's the observable I'm going to be interested in. So I want to sum over states e to the minus beta ei. So I want to solve the energy eigenproblem of these oscillators. How am I going to do it? Well, I'm going to do it like I solve any oscillator, with creation operators. So here are my creation operators. What is an eigenstate? I multiply the creation operators. I need to take a trace to get a gauge invariant state, but that's how all of the eigenstates look. This is a little misleading. I've written a single trace here. It doesn't have to be a single trace. It could be a double trace, triple trace, any multi-trace structure acting on the vacuum. But the key point to take from this is that for every eigenstate, there is a polynomial. And for every polynomial, there is a state. So counting the states, what the partition function does, is like counting polynomials. In the partition function, we weight the states by e to the minus beta times the energy. I'm going to subtract off the ground state energy. I'm going to arrange things so that my oscillator has energy spacings of 1, in which case the energy is just the degree of the polynomial. So calculating that partition function is the same as summing over the polynomials and weighting them by x to the n. So the partition function for this multi-matrix oscillator system is a Hilbert series. So that's the relevance of the counting problem. So now let me tell you some of the results that we obtained. So when you calculate multi-matrix model harmonic oscillators, those partition functions, they always take this form. And this is exactly the form that we were looking at. Sum of positive terms in the numerator divided by a bunch of factors. And for what I've just told you about Hilbert series, you should think that each factor in the denominator is associated to some generator. In fact, those generators are called primary invariants in invariant theory. And the 1 minus x to the j term is associated with the primary invariant, which is a single trace operator. So these can always be chosen to be single traces of degree j. So I've got jx's multiplied inside this trace. If you prefer to think of a daggers, think of a daggers. You'll see later why it's fine to think of x or a dagger. Each term in the numerator also corresponds to a generator, but these are the generators that we use exactly once. And a monomial x to the I, again, is degree I, but the terms in the numerator can have an arbitrarily complicated trace structure. So the space of gauge invariance takes the form shown at the bottom of the slide. It's a direct sum. Each term in this direct sum is labeled by a primary invariant corresponding to one of the terms in the numerator. And then we have a product over all of the primary invariants, and they're raised to any power which is a non-negative integer. So how should we think about this? Well, this is the structure that we're getting. There's the primary operators raised to any power, and there's each secondary operator sitting in each term. What does this look like? This looks like we're generating a Fock space by the blue invariants. This is like a daggers being raised to whatever power. And what do the secondary invariants look like? These look like non-trivial states or backgrounds of the theory. So for example, just think about normal field theory when you find a soliton solution. When you've got your soliton, you can populate that with perturbative excitations. So each of these different secondary invariants looks like a different state of the theory. And the blue guys, the primary invariants, they look like the perturbative degrees of freedom of the system. So I'm going to try to argue that these are the perturbative degrees of freedom of the dual gravity, the holographic dual, and that the secondary invariants tell us about the states or backgrounds of the theory. So we don't have a proof for that, but I'll show you some evidence which supports that interpretation. Okay, so what's the problem statement? We're going to study the dynamics or the partition functions associated with these oscillators. So 1/2 trace of momentum squared plus 1/2 trace position squared. And for D matrices, we quantize as usual. There's the normal commutator. Delta AB tells us different species commute. We've got the minus I, and we contract the matrix indices in a covariant way. Both x and pi transform in the adjoint of the gauge group, and the question we want to answer is, what is the complete space of gauge invariant operators? It's quite a complicated space, because we can take any product of these x's, take a trace, and that is a valid gauge invariant operator. What I'm aiming for, I'd like a set of generators, and I'd like to know the algebraic structure of those generators. So let's start with the simplest case of one matrix. So for one matrix, I solve the problem as always with a creation operator. After subtracting off the ground states, my Hamiltonian looks like A dagger A, and this is the answer I get for the partition function. I'll show you a formula in a few slides of how we actually calculate that explicitly. And how do I interpret that? Well, I know that each factor in the denominator should be some sort of a generator, and I'm telling you that the term with x to the n corresponds to just trace a dagger to the n. So that, for example, if we were studying n is equal to 2 matrices, we would have trace a dagger and trace a dagger squared. And that, according to this Hilbert series, generates all of the gauge invariant operators in this theory. Now, how can that be true? If we take, for example, something like the trace of a dagger cubed, that looks like a perfectly good gauge invariant operator, and it's not something that we've included. So where does the trace of a dagger cubed come from? Well, it comes from trace relations. So this is going to be the main ingredient today, the trace relations. So let's talk a little bit about that. If I have a 2 by 2 matrix, let's imagine it's diagonalizable. If I tell you what the trace of m is, I told you the sum of the eigenvalues. If I told you the trace of m squared, I told you the sum of the squares of the eigenvalues. So if you know trace of m and trace of m squared, you can solve for the eigenvalues. You can then work out, if you like, the trace of m cubed. That's what this equation over here is telling us. Once we know the trace of m and the trace of m squared, we can work out the trace of m cubed. And this equation over here is obeyed for any 2 by 2 matrix. Our a dagger is a 2 by 2 matrix, so using the trace relation, we learn that trace a dagger cubed is indeed a polynomial in trace a dagger and trace a dagger squared. So all of the mileage today is going to come out of the trace relations, and one of the things that you might think that we have done for a multi-matrix model is we have solved all of the trace relations. That's what our result does. So now let me talk a little bit more about trace relations because they'll be playing such an important role. Yep.
If I try and solve this problem using, an integral over the Cartan, say Schur style or indices style, where would I see the trace relations there? Is it easy to read it from the, there are poles that cancel, they don't have residue?
Okay, so let's see. I'm not sure I understand exactly what you're asking, but if you say Schur style, you mean like in a basis given by, say, Schur polynomials?
Well, I mean, another way is I can write all the matrices and do an integral at the end over the group, which reduces to an integral over the Cartan with appropriate measure, such that I do a very similar count. I'm not sure it's exactly the same counting, but in spirit, it's kind of similar.
So something like a Moulin-Weil formula, then, I guess.
Okay. So
that does the counting with trace relations solved.
Right, but is it easy to extract the trace relations from that? Like, is it some structure of the poles or something?
I don't think you can see the trace relations once you've got that formula. I think the trace relations have actually been solved, and this is the result after trace relations are solved.
Okay, thanks.
Sorry, I might have missed this, but with just one matrix, this is just standard matrix quantum mechanics with n by n matrices, right? And
Absolutely.
You're constructing the set of gauge invariant operators.
That's right.
In this theory, and you're able to write down the partition function.
That's right.
For this theory.
Yep.
And you have a closed form for the partition function?
Sure.
I see.
So this is just an oscillator, but yes, we do have a closed form, and I'll come to the derivation of that in a couple of slides. Yep.
I see, thanks.
Okay, so a little bit more about the trace relations. If we're talking about trace relations for n by n matrices, they are given by a sum of n plus 1 factorial terms. So I'm going to illustrate them for n is 2, 2 plus 1 is 3, 3 factorial is 6. So the trace relations should be a sum of 6 terms. And I've written those 6 terms over here. So I've written ABC 6 times. Notice that in every single term, the row indices are exactly the same. It just looks like I, J, K for every one of those 6 terms. The column indices have been anti-symmetrized. So on the first term, I've got I, J, and K. To get to the second term, I've swapped I and J, and there was a minus. For the third and fourth terms, again, I've done one swap, so there's a minus. For the last term, for example, I first swapped I and J, and then I swapped I and K. I did 2 swaps, so that's a plus. So all I've done is I've anti-symmetrized the column indices. If you anti-symmetrize 3 indices that each take only 2 values, you're going to get 0. So that's why this vanishes. And it's kind of interesting to see how it vanishes. So the sum over I, j, and k will vanish. But it turns out if you plug in any value for I, j, and k inside that sum, that vanishes. So if we plug in I as 1, j as 1, and k as 2, the first term, for example, becomes just a11, jj 11, kk 22. The last term, ij 11, jk 12, ki 21. So I've just plugged in the indices. But then you can see the first and second term vanishes, the third and fifth term vanishes, and the fourth and sixth term vanishes. So for every I, j, and k where you're summing over, each term vanishes. And notice something, this vanishing would occur if these were bosonic matrices or if they were Grassmann matrices. I didn't swap the positions of anything. So they just are completely general statements. Who cares what potential you've got? Who cares how big the couplings are? Anything proved with the trace relations is true for any potential and any coupling strings. Okay, and so I'm going to prove certain statements using the trace relations, and then I know that those hold in general for any potential in any interaction strings. The fact that you can get the complete set of trace relations for multi-matrix models in this way was proved rigorously by mathematicians in the mid-70s. It appears in a paper by Claudio Procesi. So the trace relations don't depend on anything in the dynamics except for n. So it's very important that you specify what n is, and the trace relation changes depending on what value of n you go to. Okay, so now I'd like to start studying some multi-matrix models. And to do that, I'm going to need to use the Moline-Weil formula. So what is the Moline-Weil formula? So I just want to calculate the partition function. So I'm going to set x equal to e to the minus beta. Let's imagine I have acted on the vacuum with n1 A1 daggers. Each A1 dagger will give me an energy E1. So I'll have an energy of n1 E1 from n1 A1 daggers. I'll have an energy n2 E2 from n2 A2 daggers, and so on. So these x to these factors, this is just supplying the Boltzmann weight in the partition function. And then I need to count how many invariants do I have in this state, built with n1 A1 daggers, n2 A2 daggers, and so on. So how can I do that? Well, the simplest way to do it is using characters. So let's work out the representation of this state, and then let's work out how many times the singlet appears. And so how do I work out how many times the singlet appears? I take the character for this representation, I multiply by the character for the singlet, which is just 1, and then I integrate over the group. And character orthogonality tells me I'll get the number of times the singlet appears. So how do I work out the character for this group? Well, that's straightforward. Think about the A1 daggers. Each one of those is in the adjoint. So I've taken a copy of n1 A1 daggers. Because they're bosons, I've got the symmetric product of n1 copies of the adjoint. So that's what I get from A1 daggers. From the A2 daggers, I'll get the symmetric copy of n2 copies of the adjoint, and so on. And then the character of a tensor product of representations is just the product of the characters. So this product over I with the character sitting here is giving me the character of the representation created by the A daggers. I've multiplied by 1, character of the singlet, and now I integrate over the group. The characters only depend on the eigenvalues of u. So the integrand only depends on the eigenvalues of u. So I can reduce this to an integral over eigenvalues. After some changes of variables, one of the integrals can be done, and I land up having to calculate n-1 integrals. The eigenvalues of unitary matrices have a magnitude of 1. So when I integrate over these eigenvalues, I'm integrating over unit circles in the complex plane, so I can actually do this integral using the residue theorem. So it's a very computable thing that I get. So I'm going to plug in various values of n, calculate the partition functions, and then think about them as Hilbert series, and see what does that tell me. Okay, so here's the first example, n is 2. I've called x1 x, x2 y, and just to make things clear for, in the answer, I've introduced a chemical potential for x and a chemical potential for y. So I'm using this variable little x, which is e to the minus beta minus the chemical potential for x, and little y, which is e to the minus beta minus the chemical potential for y. And if I just go ahead and calculate the partition function of this two-matrix model, this is the form that it takes. And this is exactly the structure of the Hilbert series that we were looking at earlier. So it's just a single trivial secondary invariant, and there's a total of 5 primary invariants. And from the grading, I can make a very natural guess for these 5 primary invariants. So x I would guess is trace x, xy I would guess is trace xy, and so on. So I got this set of primary invariants by looking at the partition function of the harmonic oscillator. Now what I'd like to do, I'd like to prove that every single gauge invariant operator in this 2-matrix model can be written in terms of those 5 primary invariants. And to do that proof, I'm only going to use the trace relations, so that that proof will be true regardless of what potential I have and what coupling I have. So this will be a statement about the space of gauge invariant operators for 2 2x2 matrices. So what are the trace relations? They're coming from the Cayley-Hamilton theorem, and it's this statement over here. So this is just the anti-symmetrized thing. I've just written it again. And what I wanted to stress here, I must choose A, B, and C. And A, B, and C are any 2x2 matrices, so they could be products of x's and y's, anything like that. Each one of those equations will give me a trace relation. Okay, so let's warm up and do just 2 easy cases. So let's first of all look at single traces of length 3. So now I'm looking at a trace of a product of 3 matrices. Can I write those using the trace relations? Well, this is very easy. I'm going to say I've got n x's and m y's, little n x's and m y's. And for each choice of m and n, I want to get 3 if I'm looking at words of length 3. For any choice of m and n, there's a single trace operator I can write. So for example, when m is 2 and n is 1, the only single trace operator that there is trace of xy squared. Anything else by cyclic symmetry is equivalent to trace of xy squared. And then if you look at the trace relation, the first terms in the trace relation all have 2 or fewer matrices inside the trace, so that I get trace of xy squared is this in terms of my primary invariance. So using the trace relations, I could rewrite that that length 3 operator in terms of the primary invariance. Swapping x and y, well, I can write this operator in terms of the primary invariance. It's equally easy to write down the trace of x cubed and the trace of y cubed. Those are just single matrices. If we go to n is 4, there's something new that appears, and it appears when m is 2 and n is 2. Now, in fact, there's 2 different operators we can write down. We can write down the trace of x squared, y squared, or we can write down the trace of xy, xy. And those are genuinely different gauge invariant operators because x and y don't commute. Lucky for us, there's 2 completely independent trace relations. So I could pick A to be y squared, B to be x, C to be x, and then that trace relation tells me what the trace of x squared, y squared is a polynomial in the primary invariance. Or I could choose A to be xy, B to be x, and C to be y, and then I learn what trace xy, xy is as a polynomial in the primary invariance. So just purely by brute force, I can check that all length 4 operators can be written in terms of the primary invariance. Is this possible in general? So sorry, I'm going to do some details now, but I wanted to show you what's behind our claims. So this is how all of our claims are proved. So I'd like to prove that every gauge invariant operator can be written in terms of that set of 5 primary invariants, and I'm going to do the proof by induction. So what am I going to do? I'm going to assume that if I've got k or fewer matrices in the trace, they can all be written as a polynomial in the primary invariance. I proved that statement for k is up to 4. And then what I'm going to do, using the fact that k matrices inside the trace can all be written as polynomials in the primary invariance, I'm going to prove that k plus 1 matrices inside the trace can be written as polynomials in the primary invariance. Okay, so let's start off. I'm going to look at this loop, trace x to the n1, y to the m1. So that's not the most general loop I could consider, but that is a loop I could consider. I'm going to set n1 plus m1 equals to k plus 1. I'm allowed to take k as 4, so n1 plus m1 is equal to 5. They're both non-negative integers, so at least one of them has to be bigger than 1. Let's assume it's n1. Then we'll take a to be x, b to the xn minus 1, and c to be y to the m1. Plug it into the trace relation, and this is what we get. The first term is the trace that we want to determine. All of the other terms in this trace relation have k or fewer matrices in the trace. So all of the other terms in this trace relation can indeed be written as polynomials in the primary invariance. So that proves that the first term can also be written as a polynomial in the primary invariance. Now let's look at the general operator. So the general operator will take this form. x to the n1, y to the m1, another block of xy's going all the way up to x to the nq, y to the mq. So if I've got q of these blocks of x to a power, y to a power, I'm going to call that a type q invariant. So on the previous slide, this would have been a type 1 invariant because there's only a one xy block. So for type 1 invariance, I've established the result. Now I'm going to look at the trace relation that I get from picking a to be x to the n1, b to be y to the m1, and c to be everything else in the operator. And if I just work out what does the trace relation look like, the first term is the operator that I want to determine. This is a type q invariant. The second term, n1 and n2 got together, and mq and m1 got together. So this is a type q minus 1 invariant. So you've got a type q invariant, a type q minus 1 invariant, and then on these second two lines of the trace relation, everything has k or less matrices inside the trace. So the second two lines of this trace relation, by the induction hypothesis, can be written as polynomials in the primary invariance. But I can work out the type 0 invariance, I can work out the type 1 invariant. But once I've got the type 1 invariant, I can then work out the type 2 invariant. So I can now just do a recursion on Q, and using the trace relations, this proves I can write every single gauge invariant operator in this theory in terms of those 5 invariants that I showed you. So for two 2x2 matrices, those 5 primary invariants are what replace the eigenvalues. Okay, next example. Let's look at now a model, still with n as 2, but we'll have 3 matrices. I've called them x, y, z, and I've again graded by each species of matrix. The reason why this is an interesting exercise is that this is the first time that we get a non-trivial secondary invariant. And the secondary invariant in this case looks like x, y, z. Now, in our counting rule, one of our rules was you're allowed to use the secondary invariant, but not the secondary invariant squared. Where did that rule come from that you're not allowed to use s squared? It again comes from the trace relations. So from the trace relations, with a little bit of work, you can prove that this equation holds. And what this tells you is s squared plus a term linear in s times a polynomial in the primary invariance plus a polynomial in the primary invariance is equal to 0. So if you have looked at all operators obtained as polynomials in the primary invariance plus all polynomials in the primary invariance times s, you've already got s squared. So you don't include s squared because that would be overcounting. It's already in the space of gauge invariant operators. In the general case, you won't just have one secondary invariant, you'll have many. There'll be an equation of the form Si times Sj, so any quadratic in the secondary invariance. There'll be an Sk here times some polynomial Fk in the primaries, plus a polynomial in the primaries equal to 0. So it's always the case that quadratic terms in the secondary invariance are not needed. You're already complete without including those. So you only include things linear in the secondary invariance. So for this problem, the complete space of gauge invariance is given by these 9 primary invariants raised to any non-negative power times 1, or the 9 primary invariants raised to any non-negative power times s. And that gives you the complete space of gauge invariant operators in this 3 matrix model with 2x2 matrices. And we want to interpret this as a Fock space built about the trivial vacuum, and this one as a Fock space built around the non-trivial state S. Something like a soliton state, or maybe a new gravitational background, or something like that in the holographic dual. Okay. So now let me make some general comments. So in invariant theory, these partition functions, or these Hilbert series that we found, take what's called the form of the Hironaka decomposition, and there's a Hironaka decomposition for the invariant rings. We've been calculating the Hilbert series of the invariant ring CND of GLN, or UN, you can say UN if you like, of D matrices, Dn by n matrices. And this is the structure of the Hironaka decomposition. The denominator encodes the primary invariance, while the numerator encodes the secondary invariance. Mathematicians have calculated the number of primary invariants. It's given by what's called the Krull dimension of the ring, and that's 1 plus d minus 1 times n squared. So we know exactly how many primary invariants there are. mathematicians have not calculated the number of secondary invariants. The last theorem on secondary invariants of any sort of significance was by Hilbert, and it was really just a statement of an algorithm to determine them, which was basically equivalent to the definition. So we know very, very little about the secondary invariants. Everything that I've said so far relies crucially on the fact that our partition function took this form. So how general is that? In fact, it's completely general. So we're relying on two theorems here. One is called the Rochester-Roberts theorem. What the Rochester-Roberts theorem tells us is, if you're studying the algebra or ring of invariants of a linearly reductive group, it will be Cohen-Macaulay. If you've got a linearly reductive group, how do you check? Take any finite dimensional representation. Is it completely reducible? If the answer is yes, your group is linearly reductive. So all of the gauge groups that we like in physics, UN, SUN, SON, SPN, they are all linearly reductive. So the ring of invariants for all of those will be Cohen-Macaulay. Now, what does it mean to be Cohen-Macaulay? To be Cohen-Macaulay, there's two notions of the dimension of a ring or an algebra. And one of them is the Krull dimension. So what's the Krull dimension? You count the maximum number of algebraically independent elements. So remember our polynomials made out of x and y? That Krull dimension would have been 2, because I've got x and y, those are independent, but anything else, x squared, y, or whatever, can be built out of x and y. So the Krull dimension counts how many algebraically independent elements there are. There's a second notion of dimension called the depth of the ring or the algebra. And what the depth is, it's the number of independent equations I can impose. So why is this related to a dimension? Well, think about this room. The surface of the table is maybe imposed by the equation z is equal to 1. Then I can draw a line on the table by saying x is equal to 1. Then I can draw another line on the table that says y is equal to 1, and now I'm at a point. But I can impose 3 separate conditions for x, y, and z, and that's related to the fact that we're in a 3-dimensional space. So the depth of the ring counts how many independent equations you can impose. For Cohen-Macaulay rings, depth is equal to Krull dimension. So why should we care about Cohen-Macaulay rings, rings that obey this property? The simplest kind of rings that you get are free, no relations between the generators. Every free ring is Cohen-Macaulay, but the converse is not true. There are some Cohen-Macaulay rings that are not free. So the set of Cohen-Macaulay rings is the biggest set of rings that you can think about that has the nice properties that a free ring has. And one of those nice properties, it's known that every Cohen-Macaulay ring admits a Hironaka decomposition. So for all of the gauge groups that we would be interested in physics, we know that the space of gauge invariant operators is going to take this form. Okay.
One question? Yeah.
Yep.
Sorry. But this seems very tight to the fact that the system, you're assuming like a Gaussian free theory, no?
No, because what this is related to is the gauge symmetry in the model. So when the mathematicians study this, they don't even have a Hamiltonian. All that the mathematicians say is, I'll give you D matrices, and I will have an action of GLN on those matrices, or UN for us, which is the usual adjoint action. Count how many invariants.
No, I agree with that. The invariants and the generator set will be the same. I agree, but the partition function. The point is how you distribute the energies to the different polynomials, and of course this form that you have is tied to the free case, no?
So this partition function absolutely is tied to the free case. But my logic in all of this is that what the partition function gives me is a set of invariants. So that I got from the harmonic oscillator partition function. At that point, I throw the harmonic oscillator partition function away, and using trace relations only, I prove that with this set of generators, I can generate every single gauge invariant operator. So the harmonic oscillator is just giving me a guess for the set that I start with.
Maybe to rephrase it, I mean, among these generators that act freely, there are things that in gravity you think are very, very high energy states, like a black hole, for example. So it's not fair to say that, you know, all of these other, that you're supposed to think about that as an excitation on some background. It's really
I'll
a very, very high energy.
Yeah,
you know,
I'll come to the evidence. So we certainly haven't proved it, but I'll come to the evidence for why we make that claim soon. Okay. So So the number of primary invariants is d minus 1 times n squared plus 1. But what we know is, if we look at single trace operators, all single trace operators of a length of up to n has to be included amongst our generating set. And it has to be included amongst our generating set because the trace relations only kick in when you've got more than n matrices inside the trace. So when we include these loops of length n or less, are they included as primary invariants or secondary invariants? Well, we can estimate how many loops there are of a certain length L. So if I've got L matrices inside the trace and I've got a D matrix model, the first matrix could be any one of D, the second any one of D, right to the Lth any one of D. So the number of words I can write down is D to the power of L. If I take a trace, I get a gauge invariant operator. Now that's an overcount because of cyclicity of the trace. So to correct that counting, I can divide by L. But that's an undercount because some loops have a symmetry and not all cyclic transformations lead to a distinct image. So this is an undercount, but it's actually rather an accurate count of how many gauge invariant operators there are. The thing that's important is it's growing as the exponential of the length of the operator. So if you want operators with a length of about n, the number of operators that are included amongst the invariants looks like e to the n. And this vastly exceeds the number of primary invariants that grows like n squared. So to give you an example of some numbers, for the 2 matrix model, so 2 matrices at n is equal to 20, the total number of single trace operators is 111,321. The number of primary invariants is 401. So less than 0.5% of them are primary invariants. The vast majority of them appear as secondary invariants. So there's going to be many secondary invariants that are quite short. So why should I think about these as some sort of a soliton or something like that? So let me give you a partial answer to that. What is a soliton in normal field theory? Well, it's built out of the perturbative degrees of freedom, but it's not polynomial. You know, it's an infinite series in creation operators, whatever. If you think about Sine-Gordon model, it's some exponential of a field or something like that. For all secondary operators, we can express them in terms of primary operators, and we can do that by solving this constraint that the secondary operator obeys. But you can see that this leads to something that's not polynomial in the primary invariants. It will be some complicated square root factors and all sorts of things like that. Okay. So now let's count the number of secondary and primary invariants. So I've taken 2 matrices. I've gone up to n is equal to 7. At n is equal to 7 on my laptop, it still takes about 8 days to calculate. For n is equal to 8, we did some estimates. It would probably take months. So we haven't calculated for n is equal to 8. So we only go up to n is equal to 7. We've got 2 matrices. The number of primary invariants should be 1 plus d minus 1 times n squared, so 1 plus n squared. So 2 squared plus 1 is 5. At 7 squared plus 1 is 50. So the number of primary invariants is giving us exactly the Krull dimension of the ring. Now look at the growth in the number of secondary invariants. It goes like 1, 2, 64, 15,000, 312 million, 21,000 billion. So the growth in the number of secondary invariants is incredibly extreme. So when you see that growth, how is it growing? If you do think that this is a holographic dual that includes black holes in that Hilbert space, you would expect that typical states at high energy in that Hilbert space would be a black hole microstate. Black holes should have an entropy of order e to the n squared. So a natural thing to ask is the number of secondary invariants growing as e to the n squared? So if you just make a plot of this curve in orange and the data from the previous slide in blue, that looks like a pretty good match. So something that I won't talk about, but in a paper that appeared 2 weeks ago, we gave a proof that the number of secondary invariants has to grow like e to an order 1 constant times n squared. So that's how the number of secondary invariants is growing. By the way, to get that many secondary invariants, it means that almost every secondary invariant must have a length of order n squared. And if you think about something like the half BPS geometries, the LLM geometries, those are operators created using order n squared matrices inside the matrix. They've got a dimension of order n squared. That's such a heavy operator that you have back reaction, and it corresponds to a non-trivial geometry. So in the holographic dual, we would expect most of these secondary invariants to correspond to a non-trivial geometry. So I just want to make a comment, a link to fortuity, the fortuity mechanism that's been seen in 1/16th BPS black hole systems. So there's been a big puzzle in creating the microstates of 1/16th BPS black holes. Exactly how do you build them? There weren't enough operators. And one of the key observations has, so what do you want to do? To create a 1/16th black hole microstate, you're basically solving an equation in the CFT, which tells you that your proposed black hole operator must be annihilated by a single supercharge. And there's two ways that you could interpret that equation. You could say Q should kill this operator for all values of n, and that's been called monotone operators in the recent literature. Or you could say Q only annihilates your operator for one value of n. And the way that this happens is that Q acting on this black hole operator actually gives you a trace relation. And that's why it's only valid at one value of n. So these fortuitous operators are very tied to the trace relations. The second equation, the one for fortuitous operators, is a lot less strict than the monotone operators. In this case, you're imposing an infinite number of equations. Q on O must be equal to 0 for all n. For the fortuitous operators, Q on O has to be equal to 0 for one value of n. So when you get to a high enough energy that there are significant trace relations, there's a lot more fortuitous operators than monotone operators. And in fact, most heavy operators are fortuitous, and the black hole entropy for these 1/16th BPS black holes are explained by fortuitous operators. Also, they have different chaos properties. So in a recent paper by Chen, Lin, and Schenker, Towerless times were calculated for monotonous operators and fortuitous operators. So the Towerless time, you shoot a particle off, it starts off undergoing ballistic transport, and then it deviates from ballistic transport, so it's a measure of chaos. For monotone operators, the Towerless time is n to some power. N in some systems, sometimes n squared. For the fortuitous operators, it's order 1. So this again suggests there's much more chaos, also suggests a link to black holes. And then there's another reason why this is pretty reasonable. Think again about the LLM geometries. To get an operator that back reacts on the geometry, you have to build it out of order n squared fields. So if I give you an operator in the n is equal to 10 theory that corresponds to a black hole microstate, I would have to build it out of 100 fields. Well, that operator cannot be a black hole microstate in a theory with n is equal to 100, because in the n is equal to 10 theory, it had n squared fields, but in the n is equal to 100 theory, it only has order n fields. So it's natural that something that is an operator that can be identified as a black hole microstate in a small value of n theory is no longer a black hole microstate in a higher value of n theory. It also makes us question, maybe to see black holes, we should not be looking at the strict n is equal to infinity limit. Maybe we should be looking at some large but finite value of n. So we think that we've got a bosonic analog of the fortuity mechanism. And the reason for that is, if you fix a particular value of n, and you've got a specific operator that is a secondary operator, secondary invariant, as you increase n, you get to some point where it makes a transition, and that secondary invariant changes character, and it now becomes a primary invariant. So you can have transitions as n is increased, where secondary invariants become primary invariants. And so we think about this as a purely bosonic analog of the fortuity mechanism. And in fact, if you look at the infinite n partition function, at infinite n there are no trace relations, because you have to have an infinite number plus 1 matrices inside the trace. So in that case, the partition function is freely generated, and you can see that all of the secondary invariants that used to appear in the numerator have changed character and become primary invariants. Okay, so that was basically the story. So let me tell you the summary. So what have we shown? The space of gauge invariant operators that can be constructed in a multi-matrix model, quantum mechanics, can be written in this form of a direct sum. Each term in this direct sum is labeled by a specific secondary invariant. And then there's a prefactor over here, which we interpret as building up a Fock space based on the primary invariants. The number of primary invariants is d minus 1 times n squared plus 1. The number of secondary invariants wasn't previously studied. We now have arguments that it grows as e to the n squared. By the way, this proof that it grows as e to the n squared is related to the asymptotic growth of little Wood-Richardson coefficients, which was proved, I think, 3 or 4 years ago. As n is increased, the character of invariance can change, and something that is a secondary invariant can transition to become a primary invariant. And we're putting this forward as a bosonic analog of the fortuity mechanism. So thanks for your attention.
Thank you very much, Robert, for your talk.
I want to ask you about, if I think about the SCFT, of course you have also Winston lines. So these are non-local gauge invariant operators. And also, you have open strings. So the cyclicity of the trace, it's not there. How much this goes there?
Okay, so I'm only looking here so far at quantum mechanics. As soon as I go up to a field theory, I think things are much more complicated, and we don't have anything to say there. But as far as open strings go, I mean, something that we have studied is vector models. So that looks morally like an open string. For vector models, if you have purely vector models, you expect far fewer invariants. In that case, you can actually analytically calculate how many secondary invariants there are. Instead of e to the n squared, you get e to the log number of species of vectors times by n. So it grows as e to the n. So there's a far smaller growth in the number of secondary invariants. Then, of course, for the coupled matrix vector system, well, the number of secondary invariants just explodes. So there you're back to an e to the n squared type growth.
So that was really interesting, and I realize I have several questions. I'll try to limit myself now and ask you more later. But I'm curious, you said that most of the secondary invariants are order n squared, but there are some smaller number that are not. Do some of those represent objects like D-branes, for example, and the ones that are really small, do we have an idea of what they would represent?
So we do think that those look something. So D-branes should be amongst those.
Yeah.
But then there's even other things that can happen. So for example, and you can see this for 4 matrices at n is equal to 4. There are some traces with only 3 matrices inside the trace that appear as a secondary invariant. Now what happens in orbifold models, where you've got a slightly better control, is that there are some things that would like to be a primary invariant. So that appears, but it appears as a secondary invariant. The square of it also appears as a secondary invariant. The cube of it also appears as a secondary invariant, and then it stops. So somehow there's some finite number of powers of that thing. They're all included as secondary invariants. There is no free generator associated to that thing. So at low energy, it looks like there's lots and lots of gravitons that you can raise to any power. But as you get to higher energy, these things kind of thin out and disappear, and you're not allowed to include them amongst your generators anymore. So there's probably a nicer way to describe this, maybe not quite as a Q-deformed oscillator, but something like that structure. But this is going to take away some unnoticeable fraction from the secondary invariants. Yeah.
But do you have an idea in a string theoretic bulk holographic dual what kinds of objects those might be? Are they things that we've been missing so far in string theory, new light non-perturbative things, or are they things we can understand from perturbative strings?
So I think that they're things that we thought of as perturbative degrees of freedom, but they're secretly not. So I think in the UV there's far fewer degrees of freedom than we used to think that there were.
Okay, so suppose I want to apply this to the 116. So there's some story which I haven't really worked on, so I don't really know for sure. I mean, you can write an index formula, and there's a very refined structure of what do you do with the chemical potentials, and some whole set of saddle points that you need to identify. So when you do the counting, you should see that these excited states are in one-to-one, well, not one-to-one, but in correspondence with this very refined structure of the indices. That's
absolutely. So that is a great question. That's one of the projects that we have in progress. So we're actually doing that together with Suk Kim, and really trying to show that we can reproduce the structure of those indices from these Hilbert series. And all of these details showing that they work out correctly. So that's actually work in progress. It takes a little bit more effort just because you've got fermionic matrices. And the mathematicians have not worked out very much for superrings. So even the analog of the Hironaka decomposition, you have to think through that again. So that's the step that we are at now.
But this decomposition is naturally associated with saddle points in the Moulin vial. I mean, like somehow these, these are supposed to be like some saddle points.
Yeah, no, that's a great question. I don't know. These are the kinds of things we're thinking about. Yeah.
Okay, thanks.
Okay, if there are no more questions, let's thank Robert again. And we have a break and we'll come back at 10:30.